Please be seated. I open this public meeting of the Council of Deans by expressing our faith in God. Our help is in the name of the Lord who made heaven and earth. First, I'd like to express welcome on behalf of this university to all the family, friends who've come from close by or far away to attend this particular ceremony. The ceremony is an inaugural lecture of our Professor Lora Aroyo, who will accept her chair in Human-Computer Action with a talk entitled Data Science with Humans in the Loop. Professor Aroyo, the floor is yours.
Good afternoon, Rector, Dean, colleagues, students, friends, and family, welcome. Because I always find history very fascinating, and I thought I could give you the 10,000 feet view of my own personal journey, and I hope this will enable you to understand a little bit better and get a better sense of the things I'm going to talk about later. In Bulgaria, I first developed my passion for research, then I followed it to the Netherlands, and about 20 years later, I'm still exploring it from different geographical angles. Now I thought pursuing the boundaries of time zones and bridging the academic cultures and data sciences between Amsterdam and New York, and I enjoy also experiencing research beyond the academia through the energetic team of Tagsaurus. I started with researching intelligent tutoring systems, then moved to exploring semantics for personalized e-learning, then shifted to semantic web for personalized access to cultural heritage, and then to semantic web for serendipitous exploration in digital humanities. And the most important conclusion of my work in all these areas was that to understand the value of semantic web for personalization, you have to understand people. You have to understand their ways to interact with information and consume it. As much as the research is the main part of this journey, people are in fact in the very center of it. It has been a fun, lively, and inspiring friends that made this journey a truly pleasurable one. I consider myself extremely lucky that I have met amazing women from all over the world, many of which have guided me, supported me, and shaped me as a person and as a researcher. Many of them became my role models and dear friends for life. Despite what you might have heard about the gender bias in computer science, there are also a few amazing men, which also inspired me in this journey and from whom I learned a lot and collaborated with in it. And some of them were fun too. And here again, I think for a successful researcher, it is really important to understand the privilege of working with inspiring people. The current stop in my personal journey is the crowd truth team here in Amsterdam, which I started after I joined the IBM Watson team during my sabbatical in 2012. And since then, the team has grown into a structured collaboration with IBM both here in the Netherlands and US. But enough about me, and let's take you now on another historical journey. A historical journey that describes the evolution of semantic web with its numerous influences, tracing back to some of its earliest roots, which I'm going to claim really began in the 1980s with the expert system movement, whose hype cycle led to the boom of AI in the late 80s and to the AI winter of the 90s. My own personal journey through the semantic web is intimately tied to those beginnings. So by the 1980s, with all the advances in hardware and software, the computer science broke out of the tyranny of the mainframe. Suddenly, computers were everywhere and development of actual AI systems began. During this time, the AI world was focused on experts and rules. Most researchers believe that human experts are in the center of intelligence. And to name just a few foundational examples, for example, Piero Bonisones at General Electric built an expert system for diagnosing diesel locomotive failures by interviewing the company's leading repairman in the final 2 years of his career. And the Mycin project at Stanford is the work that lives on today as the roots of Mark Muson's biomedical informatics research department, which gave us Protégé. So a large group of researchers in the 80s were drawn to the problem of how to acquire that expert knowledge. Further on in the 90s, CATS, which became Common CATS, founded by Bob Willinger and Jos Breuker, was a methodology for expert knowledge acquisition. It was about people, about their knowledge, and especially about their expertise. How do people know what they know? How can you acquire that knowledge? And it was not any particular technology or any algorithmic research that drew me here. Further, it was exactly this part, the human-centric part, that was very exciting for me. Bob's legacy was carried out further by Frank van Harmelen, Guus Schreiber, and Hans Ackermans. And somewhere during this decade, the prevalent notation for knowledge acquisition became the label graph, where the nodes were entities and the edges were relations. And then in the 2000s, the success of large-scale web-based systems and massive decentralization led in this era to a growing demand for interoperability. And thus came the vision for the semantic web. The vision was refined by a series of standardization efforts, and the knowledge acquisition community were among the loudest voices calling for standardization. They had become to encounter the problems sharing the knowledge they have gathered, and graph-based formalisms became clearly central in this. Our group continued to focus on acquiring knowledge from experts, but we began to explore new kinds of expertise, not so easy to capture using rules and declarations. And examples of such expertise are in social sciences, art, cultural heritage, and media. Studying cultural heritage, for example, requires a completely different way of acquiring and understanding this expert knowledge. And now we come to the present decade. The decade has already surpassed the 80s in excitement, investment, and hype in AI, and it has easily also surpassed it in results. Honestly, I think the future will look at this decade as the golden age of AI, and we are right in the middle of it. So, did the rebirth of AI begin with Watson? It is difficult to say, but it's also difficult to remember what was before it. Watson represented a benchmark in human question answering expertise, but it also was not built by acquiring knowledge from human experts in answering trivia questions. While Watson did use data from DBpedia, Yago, and Freebase, the idea of acquiring knowledge from experts was radically changed. For one thing, it is no longer exclusively about experts. It is also not about rules and deductive reasoning either. Today, my research is still about people, but it significantly incorporates the rise of big data and large crowds. With large crowds, we can still use people at scale to help the acquiring the knowledge hidden in the huge sources of data available digitally. Our history and legacy of expert systems, knowledge acquisition, and semantics in the form of graph have created sort of a comfort zone. A set of assumptions and rules that we rarely question, we rarely even consider, that shape our work and have created a kind of a tunnel vision. In a paper we published in AI magazine, we identified 7 myths that have direct impact on how we approach systems where human knowledge is involved. First and foremost, that there is one valid and correct interpretation of every example. Everything must be true or false. Second, that each example or statement in the graph is as important as any other. Third, when collecting human judgment, disagreement must be bad. The issue here is that it is not the disagreement that's actually bad. Disagreement is a signal of something wrong. Eliminating the signal doesn't eliminate the problem. Yet the community has been overly focused on eliminating it to show quality. Disagreement in my work has proven an important signal. We shouldn't eliminate it, we should encourage it. Fourth, our roots in expert systems have given us the tacit belief that experts are the ultimate arbiters of truth, as if they were not actual human beings with opinions and perspectives, but some oracles with universal and objective knowledge. When I say it this way, it sounds obviously flawed, but that's how we've been doing it. Fifth, it has been extremely rare in our community when acquiring knowledge from experts to gather multiple judgments on the same examples. This in part was driven by economics. Experts are often expensive, and we don't want to waste our money and want to have more data. Overlapping their work seems like waste of money, but you can also see how the previous 4 myths contributed to make it seem unnecessary. And the final 2 myths in this defining this binary world, I won't have time, unfortunately, to talk about today, but they are also interesting to consider. So, the comfort zone gave us these binary distinctions. Boil the world down to an endless series of yes and no questions, like this one. We wanted medical experts to help us understand medical texts, so we asked them a series of these questions. Does this sentence express the treat's relation between chloroquine and malaria? What do you think? Does it? And what happens when the answer is ambiguous? Look at this new sentence and recall what we've been asking. Not whether chloroquine treats malaria, but whether the sentence, either of those, says it does. And remember that the only answers you have available are yes or no. And what about this one? You can sort of see how the sentence implies that chloroquine treats malaria. That's probably what the ordinarily effective means. But how can we be sure if we don't know what it does? And here you can see the answer of an expert. But we have a good reason to suspect that they gave yes or no answers, and for the most ambiguous cases, they sort of make their best guesses. An untrained worker, annotator from the crowd, can't really distinguish themselves from the expert here. But what if we ask a second crowd annotator? And a third? It seems strange that none of them agree, and the answers keep changing. But what happens if I ask a bunch of annotators? Will a stable distribution emerge? And in all our experiments, in every case we've tried, the answer is yes. Eventually, the yes-no rates stabilize into something that my intuition tells me is more informative than what I got from experts. I can see now the agreement is higher in the first sentence, perhaps telling us that it's not clear, that it's more clear than the second. And for the last one, I now see that it's not completely negative example. It does sort of imply the relationship. So I've gotten much more information from the crowd than I did from the expert. And compared to asking a single medical expert, asking 15 crowd annotations is about twice cheaper. While all this should make sense, this simple example breaks four of the myths that I showed before. We showed three examples of sentences for which the notion of correct was different, which failed to fit equally in the true and false bins. Treating them as equal misses something very valuable. They are not equal at all. By allowing the crowd annotators to disagree with each other and collecting that disagreement, we are able to see something we couldn't see otherwise, that these sentences are different with respect to the target semantics, and we also see that disagreement is good. The annotations we got from experts, while in general of a high quality, represented one blessed perspective on the data that prevented us from seeing the spectrum of differences and getting at a more informative underlying truth. One person has trouble disagreeing with themselves, but by collecting information from multiple people, we can explore what the disagreement means and what it signals. And as we began to explore the prospects of disagreement as a signal, our analysis showed that one cause of it was the ambiguity between the different semantic relations being expressed in sentences. And this led us to the idea that to encourage disagreement, we could ask crowd annotators or experts to select all relations that apply in a sentence between the two arguments, instead of just asking them to choose one at a time. And this results in a vector for each sentence from each annotator, where the vector positions represent the relation choices and the ones indicate the annotators has chosen this relation. Many annotators annotate the same sentence, resulting in a vector for each sentence from each annotator, which we can then sum across annotators, so that the collective result for each sentence annotation is a vector like this, in which the numbers indicate the votes each relation got for this sentence. And we get something really novel here, a meaning representation of a sentence with respect to a target semantics. And we immediately see the difference between these sentences. The first one is very clear, but the latter two are different in more than just their support for the treats relation. The third one also supports another relation, symptom. And by doing this, we dispel the first myth that there is one interpretation, which really is the foundation of all the other myths. Ultimately, that the world is reducible to a set of binary distinctions. There are perspectives, opinions, incorrect and correct interpretations, shades of gray, and so on. We all know this, but our community, my community, has sort of taken this for granted for at least 30 years. And now, you might wonder where these sentences and target relations came from. We were trying to gather training data for an NLP system that learned how to extract relation tuples from sentences in order to populate a knowledge base like UMLS. This is the world's largest medical knowledge base. Although large, it is incomplete, and the goal was to expand UMLS by reading all the medical text on the web. So these relations were not chosen arbitrarily. They are relations defined by UMLS, and the Watson team identified the most important ones for the medical question answering. We call them the Super 8, and added also additional 4 rather obvious ones like ISA and part of. So looking again at the vectors, the ones that we've collected by showing sentences to the crowd, those important UMLS relations define the dimensions of a vector space. On inspection, we have seen that they encode some kind of meaning, And when we put all these things together, it should be clear that we have defined a way of projecting natural language sentences into a space defined by semantics of a database. And this brings me back to those roots of history where I began with. This is a major step towards understanding knowledge acquisition. Mathematically, what we are dealing with is a hyperdimensional space, encoded in a 3-axis tensor. A tensor is the next step in the progression from scalar, vector, and matrix. So it's a little bit like a matrix, but with more axes. In this case, we have 3, 1 for the annotators, 1 for the relations, and 1 for the sentences. And the cells of these tensors are the individual votes for each annotator, for each sentence, and for each relation. And the sentence vectors we saw already are the projection from this tensor space in the space defined by the relations, by summing the plane for the sentence in the annotator dimension. We can try to visualize the tensor as a 3D matrix, and I have done this here, but I have to point out to you that this visualization is not precisely correct, because actually the vectors form the space, as I said before, and the sentence vectors define a space in which the target relations are the dimensions of the space. In these examples, I've been using 12 relations. So the sentence projects into a 12-dimensional space. The vectors for each annotator project in a space in which the sentences are the dimensions, and so on. So this 3-axis tensor encodes the hyperdimensional space in which is the composition of all 3 high-dimensional vector spaces. So within this space we have created, we began studying the data and focusing even more intently on decoding the signals that come from this agreement, we observed something else. This agreement could come from a variety of sources. It could come from people whose bias and perspective, whose training, and also whose work habits can cause them to disagree with others, even in cases that look clear. Here, we see an annotator who just always clicks the first answer, and another one who seems to systematically agree with one another. But they both disagree with everyone else. Often, this signals communities of pockets of expertise, and while we talked about dismissing the myth of experts, I don't mean to imply that we should dismiss the experts themselves, just that we should treat them as being people. When we integrate experts and crowd, we actually find they complement each other very well. And the disagreement can also come from our target semantics. In this case, some relation defined by UMLS, while the medical experts claim to are very clear and distinct, were really not very easily expressible in human language. When the target semantics or part of it is unclear, people are inconsistent about when they think it is being expressed. And of course, as we expected, disagreement can come from sentences that express the target semantics to some degree, as in the first set of examples that I showed you earlier. Since the authors of these sentences are not writing text to populate the database, they may assume the reader already knows some relation holds, and thus they write some implied facts. And one sentence can clearly imply multiple things as well. So these 3 basic sources of disagreement fit very nicely into an old model of semantic interpretation, the triangle of meaning, due to Ogden and Richards from their famous book in 1936, The Meaning of Meaning. The idea of the triangle is that people interpret symbols and language by referencing objects in the actual world they know about. For any kind of meaning, you need all 3 parts of the triangle. And obviously, as they point out, every combination of the 3 corners are potentially unique. And reducing our problem to this diagram made it very clear that to measure the sources of disagreement, we need to understand that every corner of this triangle affects every other. A low-quality annotator who is just randomly assigning labels can cause disagreement in a sentence that isn't a sign of sentence being ambiguous. In this case, we see a very clear sentence with one vote for another relation. But when we look in the annotator who gave the vote, we see that they just voted for the same relation every time. So this spammy behavior lowers the agreement on each sentence. This specific annotator has contributed too. And although I don't show it here, will also lower the agreement on the relations. We want to lessen the impact of these low-quality annotators. And similarly, a highly ambiguous sentence would cause disagreement among the annotators that will impact each annotator's individual disagreement score. But this is not their fault in a sense. This disagreement is not a sign that the annotators are low quality, nor a problem in the target semantics. It is the fault of the sentence. So here I want to lower the impact of this sentence on the disagreement score of the annotators and the relations. And more importantly, while there are certainly extreme cases of truly bad annotators, or as we call them spammers, truly ambiguous sentences and truly confusing target relations, there are far more that are slightly bad, slightly ambiguous, slightly confusing. Here are 3 sentence vectors in order from very confusing, slightly confusing, and not confusing. And if we have learned anything so far, it is that any binary distinction is a bad idea. I don't want to arbitrarily draw a line and guess when to call something in or when to call something a spammer. In other words, the world is smooth. The history of my community came with all these traditions of binary distinctions: good, bad, expert, amateur, yes, no, true, false. The vast majority of data we deal with as data scientists does not clearly fit into such narrow and brittle categories. Smooth functions are much better and far more appropriate to the task. And in order to reflect that, I can start by measuring agreement as a percentage. For an annotator, for example, what % of the time does she agree with other annotators on all the sentences they annotated? For a relation, what % of the annotators agreed across all sentences where it was expressed? And for a sentence, as I'm showing here, what % of the annotators agreed on the relations expressed in it? And after I have a score for each annotator, sentence, and relation, I can look at the sentence vector, and instead of summing the votes, I can sum the votes weighted by the annotator's agreement score. Or even better, I can weight each individual vote by the product of the annotator and relation agreement scores. Remember the sentence where one of the annotator vote was disagreed? Now, when we weight each vote by the annotator score, and the disagreeing vote starts going away. And now suddenly, this sentence has even less disagreement. So if I measure the sentence agreement score after reweighing this sentence, the scores will go up. And so we iterate, recalculating the annotator scores by weighing each sentence, relation, and other annotators by their base score, recalculating the sentence scores, and so on and so on. We keep doing it, each iteration giving a more precise score until it converges. And what we have done here is to effectively make every score in the system dependent on every other score. The triangle becomes a dependency graph. Sentence scores depend on annotators and relation scores. Annotator scores depend on sentence and relation scores, and etc. And I really hope this all makes sense. It has a nice mathematical foundation as well. It gives us a way of measuring ambiguity and annotator quality. It gives us a more flexible and sensible way to transform language into these annotators and into these knowledge graphs by projecting through a space defined by sentences, annotators, and relations. And it is accurate. The intuition that there are many intermediate cases, the low-quality annotator who isn't quite a spammer, the vague sentence that sort of express what we are looking for, the semantic relations that are a little ambiguous, they all can be seen when we measure it. It is a spatial representation of meaning that harnesses disagreement. We end up with more reliable data. Data gathered from the crowd is as good as, or even better than the one from the experts. And the data we collect ends up being a better source of training for machine learning systems. We have done many experiments to measure the advantages of this approach. This one, for example, shows that an NLP system trained with our method performs better than a system trained with binary labels provided by experts. And I'm talking here about medical experts. Oh. And this one shows a little data science to support our claim about reliability. When you see binary labels for the whole range of slightly true cases, you are just drawing an arbitrary line somewhere and saying these are in and these are out. In our experiments, we found out that our measures of sentence clarity were highly correlated with the classifier getting the right answer. In other words, more ambiguous sentences were much harder to classify. And we have done experiments in different NLP domains on tweets, news, articles, video descriptions, medical text, and so on. Here we show that across all those tasks, the crowd truth method performs better than any other. And not only does the crowd delivers results at expert level quality, but it's also a third of the cost. And the really exciting thing is that it's not just about natural language processing. We have tried it also with photos, videos, sounds, etc. And I always like to go back to our first crowdsourcing experience. This was the video tagging game Vajda to gather time-based annotations on videos and thus improve the online video access. It provided us with lots of insights that later inspired crowd truth and began another inspiring collaboration with the R&D team at Sound and Vision led by Johan Aumann. I consider them true frontrunners in their field. With the Dive Plus exploratory search for heritage collections, integrating collections from the Rijksmuseum, Royal Library, Amsterdam Museum, Tropen Museum, Sound and Vision, and NIOD, we also apply crowd truth for acquiring events as annotations and their ambiguity and granularity problems. And in our current collaboration with IBM and Maurits Huis, we explore question answering in art. And I will let you hear them talking about it.
The anatomy lesson of Dr. Nicolaas Tulp is the perfect place to start. It's a very important painting, a key painting in the development of Rembrandt's work. Thinking about Rembrandt, it became even more interesting because sometimes expert opinions are divided, they may not always be the same, and we realized that Watson could deal with ambiguity, could deal with different types of opinions.
So, and now to another example. At Google, crowd truth helps understanding the same kind of interaction as I showed with relation extraction, here between users, maps data, and questions about places on the map. This resulted in more than 8% improvements in coverage, and we are talking here about hundreds of millions of questions about places everywhere on Earth. Another example, at the New York Times, crowd-truth metrics improved significantly the accuracy of their emotion predictor for news articles. So over the years, our work profiled as user-centric data science at the forefront of what technologies can do with data at scale in a diverse set of domains. And I would like to take a short glimpse in how our future might look like. The first thing that we actually did to reflect the research challenges we changed the name of our group. And from Weapon Media, we now call ourselves User-Centric Data Science. And to go where no one has gone before, next we aim to apply crowd-truth for repurposing and reusing digital TV content, help broadcasters decide when, in what form, and in which platform to deliver which content. And to deal with truly challenging topics, we join effort with digital humanities and social sciences for improving detecting fake news or propaganda messages from biased media sources by means of applying crowd-truth. And finally, what I've tried to tell you is that crowdsource is a different way of thinking about truth. It embraces the notion of disagreement, and it treats it as a signal. Crowd-truth allows for more continuous and spatial formalization of truth that is much better aligned with common sense, human semantics, and reality. And therefore, I think it really rocks. Getting to where we are right now with our work required moving out of our comfort zone and our traditions, and I expect many others will disrupt their own comfort zones in this way in order for all of us to reach the tipping point in terms of understanding ambiguity and context. There is a lot of fundamental research still needed here. And before I finish, I would like to thank all the people that over the years supported me in my journey. In the last 11 years, our department became truly collaborative environment and a unique place to work. I'm grateful to have been part of this process. I express my gratitude to the management team of computer science, the faculty of exact sciences, and the board of the VU for acknowledging the importance of people and their interaction with machines as essential in achieving the connected world vision, and for providing me the opportunity to work in this stimulating environment. I extend my gratitude to our colleagues from the Center of Advanced Studies at IBM Benelux who continuously support the development of crowd-truth ideas. Special thanks go to Robert Jan Sips, Zoltan Slavik, and Gerrit Smit for their tireless effort to make the collaboration between VU and IBM reality. Thanks to Professor Darina Dicheva, I had an excellent entry into research. Thanks to Professor Paul Debras, my transition from PhD student to an assistant professor was very smooth, and he supported me in many ways beyond research. Special thanks to Professor Schreiber for being an extraordinary mentor and a unique role model for me. And I want to thank all my friends spread all over the world who experienced all the ups and downs of my journey. I'm especially grateful to the ones who made it here today. My final thanks goes to my family, my parents, who taught me to appreciate the value of knowledge, the beauty of nature, and the spirit of traveling. My sister, my best friend and true mentor in appreciating art in all of its forms. And my nephews that are a good reminder for me all the time for staying open-minded. And a very special gratitude goes to my husband, who is my true soulmate, both in research and in life. We share the creation and the evolution of crowd-truth vision. Thank you for your patience and understanding for all my oddities, stubbornness, and continuous working during holidays and weekends. Your love gives me wings. Ik heb het gezegd.
Thank you, Professor Aroyo, for this very nice speech. I must admit, although not allowed, that during your talk I was monitoring, unlike other times, I was monitoring the Twitter stream. Not a social media person, but I was sure that we would find somewhere a tweet from our illustrious colleague at the other side of the Atlantic, President Trump, who would tweet something in the like, fake science. Finally, it's shown that humans do better. So, unfortunately, nothing like that happened. No fake science here. Although you've shown quite a lot of interesting things that normal non-scientist people can do. The topic of your talk is intriguing, and the topic of your work. It's a topic that's an important niche in this era of machine learning. You've shown that you can do complementary work from a different perspective. It also challenges the whole bit of almost old-fashioned, very systematic thinking in computer science, where we think of categories as something that are stable, that everything fits into one or another category, that the boundaries are complete. You've shown us that the insights that, for instance, you have in cognitive psychology from the people like Roche you can apply them in the area of computer science. That's also you've created this notion of disagreement as a positive thing, which really reminds me of the old Hegel-type view of science as a true arena of dialectic debate. So a really challenging subject you've chosen. This subject also is inherent to it are the links to other parts of this university. You've mentioned digital humanities, so there are clear links into other areas, other disciplines, social science, biomedicine, that are apparent in this, and that medicine itself. This is important for a university that wants to look beyond the borders of discipline and also teach this kind of broad thinking to students. By the way, thinking of the mission of our university, the whole minority thing, the minority vote, and the importance of that is also an important distinguishing feature of your work, and I am proud to say also of this university. Your work has also created links to other important partners in this region and outside it. You've mentioned IBM and Google. I also mentioned important musea like the Rijksmuseum and archives like Sound and Vision. This is important for us as a university to be able to stand in this society, to be relevant to the society without jeopardizing our research. You've also shown that your research is of high quality. You recently acquired a very prestigious Horizon 2020 project. Projects have become very difficult to get, and that's a big praise to you as well. So, as a university, we're very proud to have you in our midst. I'd like to extend my congratulations to your family, to your friends, to your husband, Chris. Also, I'd like to congratulate the Department of Computer Science with this strong new professor in your midst. And I'm happy as a faculty to welcome you as an important senior member of this community. We have now come to the end of this ceremony. Before I'm closing, I'd like to ask you, when we leave, to give precedence to the people in the first rows following the beadle. I would like now to close this public session of the Council of Deans by pronouncing the doxology. Please stand. the name of the Lord be praised from now to eternity.